Okay, so remember for day 2, we are going to be looking at solving these riders, right? And then this is the background knowledge that we need, right? Because in grade 9, we need to know those fun angles, which we are going to look at in a few seconds. And then grade 10, we need to know the properties of quadrilaterals. You know, Euclidean geometry, like I told you, these riders, they combine everything. So we need to know the properties of quadrilaterals. And then from grade 11, we need to know the 9 theorems that we have for circles. And then grade 12, we need to know the proportionality theorem. But I'm only including proportionality for today, which I'm hoping we'll get to, right? If we don't, then it means we'll have to do proportionality and similarity tomorrow. All right, so getting right into it, right? I think we remember when our teachers told us in grade 9 that maths is very much fun. And I also believe them. I hope you also believe them. And yeah, it is indeed fun. But when they were showing us these 3 angles, they wanted to tell us that they are fun, right? I know that they didn't tell you the full information about them. They would just say to you, maths is fun. They tell you these are corresponding, cointerior, and alternating. But now you're in grade 12. So because you're in grade 12, we need to dive deep into these fun angles. So the first ones are here. You can see these are the corresponding angles. So this is an F shape, if you can check. This is an F shape, isn't it? And then now on that F shape, the angles that are formed like this one here, which is alpha and beta, those 2 angles, right, we call them corresponding angles, meaning they are at similar positions on those 2 lines. But those corresponding angles, right, I'm now using alpha and beta because I'm talking to grade 12s here. I'm talking to people who now know. In fact, even grade 10s and 11s, they know that we use symbols such as alpha, beta, and theta to represent unknown angles, right? So here I'm using them just for visualization purposes. So alpha here will be equal to beta. But why? Because those are corresponding angles. But they are only equal if these 2 lines here, AB and CD, are parallel. So that is why we always say that we are saying that these angles are equal because they are corresponding angles, and also because AB is parallel to CD. Because you must understand this. If I drew this thing, and then let's say AB was this side, and then BC was here. Oh, let's call it CD. Tell me guys, if I have an angle here, I'll call it alpha, and then an angle here, I'll call it beta. By just looking at them, can you say those angles are equal? By just looking at them. Now I don't see them being equal. Right, I don't. Because you can see, Loena, this line here is like slanted a bit far away from this one. And then compared to this angle beta here, they are not equal. So these are still corresponding angles. Please note the alpha and the beta here, they are still corresponding angles. However, they are not equal. They are still corresponding angles, but they are not equal. Why? Because line AB and CD are not parallel. So corresponding angles are only equal if the 2 lines are what? Are parallel. Now we know that it means the lines must have the same distance between them, right? Then the angles that will be formed here would be equal, the corresponding angles. All right, I hope that is clear. And then the other ones that were not usually shown, right? I did a bit of an extension here to say we can also have corresponding angles here as theta, and then as, what is this symbol here? Can anyone tell me this symbol? Zanzang. What's the name of that symbol there? There. Okay, so those angles are not equal. They are not the same, right? The names of the angles. This one we call it.
Sir,
Yeah.
That symbol, I've seen it when we're doing, what's this? What is that? Electrodynamics.
Oh
The
yes. On Faraday's law.
yes.
N change in phi over change in t. We usually call it magnetic flux, right?
Yes.
Yeah, luckily you are speaking to a physicist again. So that symbol we call it phi.
Instead of a car, what do I get?
But you didn't tell me the name. But you didn't tell me the name. I understand where you found it, right? I understand where you got it. I applaud you for that. At least you know that I've seen it somewhere. But the name though, right? The name is pricey. You know what they say, the name of a person costs. Even the name of this one costs a lot. So that is your phi there. And phi is equal to theta. Still, because those are corresponding angles. They are at similar positions on these two lines, right? And then this is because AB is parallel to CD. They're only equal because the lines are what are parallel. Good stuff. So let's see the position of those corresponding angles. Please remember those positions there. Even if I were to extend here and extend here, these two angles here would be equal because they are between parallel lines, and then these two angles would be equal because they are between parallel lines. Okay. Next, we have alternating angles. Fun, the U part, right? Now, I was using those symbols so that it is very much visible or clear that when you move from corresponding angles to co-interior angles, instead of saying that the angles are equal, we instead say that the angles, when you add them, you get 180 degrees. The angles are supplementary. So here is alpha here, and then here is beta. When you add them, you're going to get what? 180 degrees. But that happens only if AB is parallel to CD. So your co-interior angles, they are called co-interior angles, but they are only supplementary if the lines are parallel. Which means that, I want you to look at this, guys. Logically, lawyer, you will tell me that, hi, but lighting, how can these things be equal to each other? Check these two lines. I'll call it AB here and then CD. These angles, they are co-interior because they are inside of this U shape. They are co-interior angles. So please, A and B are co-interior. But those co-interior angles, can we say when you add them, you will get 180 degrees? No, that can't be. They cannot give you 180 degrees. I'm sure they give you more than 180 degrees. Why? Because the two lines are not parallel. Okay, but when the lines are parallel, when you add them, you'll get 180 degrees. Good. I hope that is okay. Just remove this part only. Yeah. And then look at again your theta and pi. So what I did here is that I actually said if we join these two again on top here, I know that in grade 9 we don't usually do that because we don't want to confuse the learners, but I believe you guys, you know now, right? You're much grown-ups now, right? So here, if I were to put a dotted line and form two angles, those angles will still be co-interior angles, and when I add them, I'm still going to get what? 180 degrees. So this is because your co-interior angles are supplementary, provided that the lines are parallel. Which means when you add them, you get what? 180 degrees. Good. And then lastly, we have alternating angles. So alternating angles, right? These are angles that they usually say they form a Z shape. So here I also used the symbols alpha and beta so that you can clearly see that I'm saying they will be equal. Why? Because these are alternating angles, but they are only equal. The real reason why those alternating angles are equal is because the lines are parallel. So yes, they are alternating angles, but what makes them equal is because the lines are parallel. And then same with pi and theta there. They will also be equal. Please take note of the positions. Right. Take note of the positions. Let me test you a bit. Let's say I were to put an angle here, and then I would call it Z. Can you tell me which ones are co-interior angles on this shape here? Anyone?
P and beta.
So you are saying here, if I were to say that phi plus beta, they will give me 180 degrees, and those would be your co-interior angles.
Yes, no.
Okay, someone says no. Talk to me.
Sir, you're saying, you see, no, Z plus beta and
Z plus phi plus beta, they will give you 180.
Yeah.
Those are your co-interior angles, right? Because AB is parallel to CD. Great stuff. So when you add those corner angles, all of them, they are the ones that will be your co-interior angles, and they will give us 180 provided that the lines are parallel. Good stuff. Good. Are we all okay here? I think I've just rejuvenated your mind a bit. I know geography students, you understand me when I say that. So I hope I've just rejuvenated your mind in terms of the fun angles. Guys, are you sure you understand these angles? Can anyone maybe, can you, maybe by a show of hands, right? Can you tell me that, can you show me whether you understand this? If you don't understand, then don't put an emoji or raise your hand. I will know that someone does not understand one of the fun angles. So now that we understand this, I want to test whether really we do understand. Right. Here's some practice questions that I got for you guys. Let's see if you are able to identify those angles. Right. How are we going to do this? Oh my goodness. I'll just allow you guys maybe to kind of like assist me in identifying these. Then if I feel like there's this one that I like, then we'll also talk about it. Okay, so let's look at the first diagram, good people, this one. Looking at this diagram, which angles can you identify them from the angles we just spoke about?
I can see alternating angles.
Alternating angles. Which one and which one?
I don't understand. What do you mean which one and which one? BCA will be 65 because of alternating angles.
Now you get my vibe. BCA is equal to EBC, and both are 65 degrees. And you are saying alternating angles. But your reason is incomplete. Which lines are parallel?
EB and DA.
EB is parallel to DA or AD. Great stuff. Great stuff. Any other angles we realize we see there?
Whereas we can get angle A.
We have a U shape, we can get angle A. So which pair did you identify in terms of the U shape? So you're saying you found coincident angles. Which one and which one?
I don't understand the question.
So the question will be, or rather, when you give me these angles, right? What I'm just looking for in these questions, right, is just to tell me if you are seeing maybe a pair of coincident angles. For example, let's say you see that these and that are coincident angles. I just need you to give me those coincident angles without necessarily solving anything. I just need to know those angles. I don't know if you get me. So you would say maybe EB or BEBA or just angle B, right? So you'd say angle B, the whole of angle B plus angle A should give us what? 180 degrees. And then you would tell me, okay, this because these are co-interior angles. And then you name the lines that are parallel. You tell me EB is parallel to AD. That's all I'm looking for. You get me, ma'am?
Yes, I do. Yeah.
Good. Any more angles you then maybe can identify there? Yes.
I have a question.
Talk to me.
So the angle that I just said is 65. Why can't we say it's 32, then we say vertically opposite angles?
That's a good question. That's a very, very good question. But ma'am, according to you, you said it's 65, which I believe is very much correct. This is just an error on their part, okay?
Yeah.
It's an error on their part. It should mean that actually this one is vertically opposite angles, so it means this is also 65.
Okay.
Great stuff, great stuff. Okay, so any other maybe a pair of angles that you identify in terms of one of the fun angles on this diagram before we move to the next one? Same.
5 corresponding to the C.
The B under 65 corresponding to the C.
Yes, sir.
Can you name them so that maybe I know which angle is that?
EBA.
EBA. So you are saying this whole angle, which you can, yes? It's equal to which one, or
Is corresponding to FCA.
it's corresponding to FCA. Okay.
Oh no, sir. It's CBA is corresponding to FCA.
That's correct. That's the one I wanted. Oh, so this one, EBC, right? EBC, which is the 65, right? We can say it's equal to the DCF, and both should be 65 degrees. Why? Those are corresponding angles because EB is parallel to AD. Okay, good stuff. So actually this one and this one, they are corresponding angles. And if I can try to draw like something like an F shape there, oh, let me try. They make an F shape. Look at them, right? Look at this. And then look at that. It's like a slanted F, which takes us back to what we had here on this one and that one. So it's like an F that is looking that side, and then these angles are equal. Check it here. You see? So it's like an F that is looking that side, and then the angles in between there are equal. So those are your corresponding angles. What I want to do is to foster a skill of always being able to identify these angles when you are given the parallel lines. Right, another angle that I do see here, right, which is I don't know if you will agree with me. I want you to check out this one. Is it there? Let me see. It's not there, Shane. It's not there. All right, it's fine. So these angles, all of them, those fun angles, are just angles that are formed by you drawing a line between the parallel lines. Then you form those angles. Okay, so that is it there. Let's go to the second diagram. Any angles that you identify them?
ABE corresponds
ABE. Okay, this
yes, is a co-interior angle with DEB.
DEB with this one. Oh, yes, that's true. That's true. It's a good one. So ABE, right, plus DEB, they add up to 180 degrees. Why? Because those are co-interior angles. That is a good one. Why? Remember this, because AC is parallel to DF. Great, that's a nice pair. Any other pair? Miss Masupe. Yes, ma'am.
Yes, you're pronouncing it right.
I'm from. Hey, low self-esteem.
Yes.
I'm sorry.
Don't
Right.
doubt. Angle C
Mm-hmm.
and plus angle D must equals to 180 co-interior angles.
This one and this one.
Yes.
Good, good. You know, when you said angle C, do you know where I first looked at? I looked at
That one. I see. I'm sorry.
No, but
And then
mm-hmm. So can we maybe name it using the lines? Aha. Try naming it
Okay.
using the lines. Nice.
okay. CBE
CBE. This one.
plus BEF
Plus BEF. CBE plus BEF. We get 180.
yes.
Oh, nice. Those are our co-interior angles. Which other ones do we see?
Then C should I go again?
Yes.
CBE
CBE. So meaning this one again.
yes
Mhm.
will be equal to BED
Will be called to.
alternating angles.
Oh, nice, nice. You see, for these co-interior angles, I think I shouldn't be using these circles, because these circles usually we use them to say the angles are equal. So please excuse me or forgive me there for using them. But this angle here, ma'am is saying it's equal to that. That's very nice. So what are those?
Alternating angles.
Alternating angles. So we have CBE being equal to BED. Right. This is because these are alternating angles. Any others that you see?
Then ABE
ABE. So meaning this one?
yes will be equal to BEF alternating angles.
Aha, would be equal to BEF. Would be equal to BEF. Those are our other alternating angles. So that's A, B, E, right, being equal to B, E, F. Alternating angles. Nice, nice. Great. That's true. That's very true. Any others we see? Any other angles there? You identified a lot of them, eh? Yeah, that was quite a lot. And that is very true, guys. Trust me, you're doing very much well. These are indeed our pairs there, our fun angles. Yes, ma'am.
Say, since like we are done with the angles, I wanted to ask if B, the small b is equals to A since the sides are equal.
If the small b is equal to A, since the sides are equal.
Yeah.
Yes, that is true. A here is actually equal to B. And I think we talked about this yesterday. We said what is going to be our reason?
Angles opposite equal sides.
Angles opposite equal sides. Because GB is equal to GE. We're using it a lot when you're proving, so that's a very good observation there. Nice. Okay, that all the fun angles we have identified there. And actually, you would use this to actually answer the questions, right? For example, look at 34 degrees, right? 34 degrees and A, right, would be equal to this one here, which is D, right? But you also said C was equal to this BED, right? So that will be your C there, and then you have your E. Oops, right? Because this question actually was asking us to find the angles A, B, C, and D. So you would use that information to find those angles. Would you be able to solve this? What I can tell you is that, of which is something we're gonna go over. What I can tell you is that this is 48 degrees. So you must understand that since A and B are equal, that means you're going to say, right, if you were to solve that, right, you would say 48 degrees plus A plus B should give you 180 degrees. Remember, those are sum of angles in a triangle. Then remember, A and B are equal because these are angles opposite equal sides. You are more than welcome or allowed to write that as 48 degrees plus 2A, because B is still A. So you could write that as 2A is equal to 180 degrees. Then you could solve for A. After getting A, you now have your B. Okay, after having B, you can get C. How? Because those are angles on a straight line. Okay, those would be angles on a straight line. Then you would get C, and you already identified that C is equal to B plus E. Then you can get E. Then lastly you would get D. But then I'm not really into the solving part for now, but I just wanted to show you that we can actually get all those angles, right? Good. Just a bit of more practice on these. Now let's say I have these two figures here. Can you identify the angles here, our fun angles on this diagram? Let's start here first. Yes, ma'am.
I can see alternating angles.
Which
I
one?
can.
Which one and which one?
Oh. LKM
LKM, which is the one? LKM.
will be equal to KMN.
So LKM, let me just say, this is this one, would be equal to KMN. So it will be equal to this one. All right. Will be equal to KMN. Those are your
Alternating.
Which lines are parallel?
LK is parallel to MN.
LK is parallel to MN. Great stuff. Great stuff. Those are the alternating angles. Next.
Sir,
Uh-huh.
I see that LKM plus 2x
What's
is equals
2x?
to H is M
It's
is M
M.
H. It doesn't have the three things, but then it's 2x.
How is it an angle if it doesn't have two sides? It must be formed by two sides. Look at the two sides forming the angle. I agree it's this one.
Yes,
So can we say it's formed by KM and ML?
oh, yes, LKM and LMK. When you add them, they give you 180.
What's your reason there?
I think it's co-interior.
Co-interior angles. Are they? Are they co-interior angles? Do they form a U shape? Yes.
Can I ask, when you extend the line MN, I guess it's going to be a U shaped that is looking downwards. So is it right for us to say that they are co-interior?
But you would have said LMK. What about this small portion now? So that this and this are co-interior angles.
Oh, okay, see.
Now, thank you so much for that. That brings me to one of the most important points when we're dealing with proving. Never construct. We only construct when we're proving the theorems. But when you're solving the writers, we do not construct. Hope that's good there. Yes, ma'am?
Okay, I see two more angles.
Which ones are they?
I see corresponding and co-interior.
Corresponding and co-interior. Which ones would be corresponding?
KLM and NMQ.
And NMQ. Great stuff. They do form an F shape. Look at them. They do form a nice F shape there. Right. Good stuff. Those are corresponding. Let me just jot them down. Yes, then you can continue.
Then KLM plus
you said K
KL
again,
plus,
okay?
yes, plus that whole okay, ML.
That whole ML.
I realized that me saying the whole M wouldn't be mathematically correct, like what I was about to Yes.
So
For the co-interior one. So it's NML, that whole angle, the LMN.
LMN.
Yes. NML.
So it's this one.
Yeah, the whole one.
That's true.
Co-interior.
That's true. You see, they make a U shape there. Right. Yes, your U's are going to be slanted, the F's are going to be slanted, but it is still a U shape, right? Perfect. So it means plus LMN, that should give us 180 degrees. Those are our core interior angles because LK is parallel to MN. Good stuff. Any more, any other angles that we see? Come on, guys. Let's go. Yes, ma'am.
So I think angle L is equal to angle M.
Oh, so you're saying angle L, which is this whole angle here. It's equal to
No,
which one?
angle L.
Which is this whole angle here?
The whole angle.
Which one?
The L which is inside a triangle.
The L inside the triangle. Yo, yes, ma'am. I like your argument. You see, if you go on a debate, trust me, you are gonna win. You are going to win. Check though, right? If you say L, this is because, right? Check, L is L1, and also it's made up of L2. So this is why you're going to have a diagram sheet, and that diagram sheet you can put these L1, L2. You're more than welcome, so that you use them like that. Ne? We cannot call it L because L is the whole angle now. L is the whole angle. But if you want to talk about this one in particular, just look at the lines that make up that one. It's this line and that line. Then what you simply do is to follow those lines. So meaning that you would say what? You would say KL, then put a cap on where the angle is at the bottom, like you said, and then you say M. Then you are saying it's equal to, it's going to be equal to what?
NMQ.
Aha, good. Now you are following me. NMQ, right? NMQ. Then what is your reason then?
Corresponding angles where KP is parallel to MN.
KL, right? It's parallel to MN, isn't it? KL. The lines that are parallel, this one and this one. You see? And then our F shape would be here. This is where the F shape would be. So the angles would be this one and that one. I so hope you can see that. Are we okay? Sorry. Okay. Miss Vanessa?
So I think I saw another angle, yeah.
Talk
Yeah,
to me.
correspond.
It's
NML.
NML, this one.
Yes. Is equals to KLP.
Is equal to KLP. Perfect. NML is equal to KLP. Perfect.
Yes.
Those are what? Your corresponding angles, right? corresponding angles. This is because, remember, this is because LK is parallel to.
Yeah.
Great stuff. Thank you so much, ma'am. Thank you so much. That is a good observation. So you can see we found all our angles there. I think they are all, guys. Yeah. Miss Lady, do you see any other there? I don't see any.
No, sir.
Did we say NML plus KLM? LM, and yeah, no, they are all good stuff. You are doing okay, guys. Okay, now let's, you know what I did, right? It was a nice transition from just looking at the angles on their own when they are between parallel lines, and then now taking them inside of a circle. Now here we are inside of a circle now. Can you still identify those angles? Let's go. Let's go. So in the diagram they told you that, remember that the statement said PR is parallel to QB. This should be your, whenever you see PR is parallel to QB or these lines are parallel, that is where, remember, you're going to find your fan angles. Now, which ones are they? Can you identify?
Sir, since line PR is parallel to a line QB, angle PRT is equals to QTR. Is plus.
Okay. So you are saying PRT, right? Plus plus QTR. They equal to 180 degrees. What type of angles are those?
Co-interior.
Perfect. Those are co-interior angles. And this is because our lines, which one? PR is parallel to QB. Perfect.
So, another one.
Another one. Okay, yes.
So, we have RPB equals to a QBP.
Huh?
QBP.
Oh, this
yes.
one. All right. Why
alternating angles for PR is parallel to BQ.
Great stuff. So that would be PBQ, right? They are equal because those are your alternating angles, because PR is parallel to QB. Great stuff. Give me more, guys. Yes, ma'am.
RQ.
PRQ. Let me try to locate it. PRQ.
I mean, sorry, yeah, Q, not O. PRQ. Is equal to. Oh my God. RQB.
RQB. Good. Can I do this, guys? For those that are equal, can I put double lines, right? And then for our corresponding angles, can I just put single lines so that we differentiate between the equal ones and those that add up to 180? Can that be our little secret there? Is that okay?
Yes.
Okay, good stuff. So you just said to me, ma'am, that you said PRQ, right? PRQ is equal to RP. RP.
Sorry, I can't see more. PRQ is equals to RQB.
RQB. What is your reason? Oops. Okay, just a second. Right. Alternating angles, because PR is parallel to QB. Great stuff. Right. Now, any more angles that we are seeing there, good people? And please do remember, the ones that are double shaded, those are equal, and then the single ones are co-interior. Good. Yes, ma'am?
Say it's PQT.
PQT. So this whole angle here.
Yes. And then RTB.
And then RTB. This one here.
Yes.
Wow. I could have never thought of that. Yeah, are they equal, those ones? Let me check.
That's what I'm asking.
Are they equal?
They should.
Are they between parallel lines? Oh, remember, if you are saying they are F-shaped angles corresponding, right? So here is the F here. But I want you to look at the lines that are making up that F, right? I want you to look at PQ, then I want you to look at RT. Are those lines parallel?
Yes.
PQ, check it. PQ and RT. Remember, we only told
they're not. The only parallel lines are PR and QB.
PR and QB. So they can't be the same. It's okay that you identify them as corresponding angles, but remember they won't be equal because the lines are not parallel. Okay. So, any other angles, guys? I still see some angles, so I'm hoping you'll be able to see, guys. I know it's a bit complicated diagram, but I trust you guys.
Yeah. I think RPQ.
This one.
Yeah, plus EQP. They add to 180.
Oh, nice.
Sir,
Yes.
Interior angles.
sir. PRS is equals to QTS.
PRS would be, let's see, PRS. This one is equal to
QTS.
It's equal to QTS. That is very true. So
Corresponding angles.
corresponding angles. Remember, we use double lines to indicate that those are equal. So let me write it here. So that will be PRS is equal to QTS, because those ones are your corresponding angles due to the parallel lines. They're equal due to the parallel lines. Okay. I think we have exhausted all of them, eh? Anyone who still sees something there? I think we have exhausted them. Okay, that's fine. So as you can see, these are a lot of angles. that we have managed to identify, right? Which is very, very nice. Because it's a very nice skill, very, very important skill. Right. Just a bit more, right? A bit more to see how far we are. Here's a diagram here. We have some chords and the likes. They tell you this statement, this beautiful statement here. They tell you that AC is parallel to DB. Which lines are equal?
So we have CAB.
CAB
Is equal to DBA.
is equal to DBA. This one here.
Alternating angles.
Great. So CAB, we use double lines. So CAB is equal to DBA, alternating angles.
So angle ACD is equals to angle CDB.
Is equal to angle CDB. Oh, that's nice. What's our reason?
These are alternating angles.
Those are alternating angles. That's great. Any others? Can I not say this is equal to this corresponding angles? Would that be true?
No, sir.
That wouldn't be true. Well, the reasoning is not true, but later on we find out that actually but the angles themselves are equal. Okay, this is good, guys. This is very, very nice. Truly speaking, those are the only angles from the fun angles that we have. Perfect. Just a bit more. Which angles would be equal here?
So E
B
E T C
ETC. This one
is equals to C1.
is equals to C1. That's great. What's your reasoning there?
Alternating angles.
ETC, which is also T2, right, is equal to angle C1, alternating angles.
Then ACB is equals to TFB.
ACB is equal to TFB. This one.
Yes, sir.
What's your reasoning there?
I think corresponding.
I also think so, ma'am. BFT. So those are our corresponding angles. Yeah. Or angles that we see.
T1 is equals to C2.
You came with a nice one there, ma'am. Quite interesting one. T1 is equal to C2.
Yes, sir.
What would be your reasoning?
I think alternating.
Okay, let's try to form the Z shape there. The Z would be going like, it starts here, and then it goes to this one, and then it goes here, and then it goes there. Now, yes, indeed, those are Z angles, but is the line TA parallel to the line FC?
No, sir.
Askies. Right. Very good observation, though. Right.
So say I'm not sure. Will I be wrong if I say EFC?
EFC, this one.
Yeah.
Mm.
And then Yana is equals to FCA.
Wow, that's very much perfect, ma'am. That's very much perfect. They are still Z angles. Look at them. Your Z, yes, it will be a very, very ugly Z, but, or your N, it's a N or Z angles. But the fact that FE is parallel to AC, that means those angles are alternating angles. And which makes sense because, remember, this BCA, the pink one, was already equal to this one. And this one is vertically opposite to this one. So which makes sense that this one should be equal to that one. Good stuff.
Okay.
Right. So that is, oh, let me write it here. EFC, right, is equal to FCA. Alternating angles, because they are equal because T is parallel to AC. Good stuff. Any more that we can identify?
Sir, TFC plus
TFC. TFC. Okay, this one.
plus ACF
Plus AC.
1/8.
They add up to 1/8. Okay, that is true. That is true. TFC plus FCA, they add up to 180. Those are our
Co-interior angles.
co-interior angles. And it's because, right, they are between, it's a U shape between TF and AC, right? So TF is parallel to AC, or you can say TE is parallel to AC. Good stuff. Are they all?
A, say, A is equals to A T. They add up to 180. This one is ATF.
ATF. Oh, so you're saying these ones here, they add up to 180.
Yes, sir.
Okay, that would be how do we call this? Let's say ETA, right? Plus angle A, they add up to 180, and then those would be your co-interior angles. Co-interior angles. Right. Another
Sir,
one. Yes, ma'am.
A is equals to T3.
A is equal to T3. Why do I
Yes,
feel
sir.
like you guys took a long time to realize that one? A is equals to angle T3. Good stuff. Those are our
Corresponding angles.
corresponding angles. Good, because TE is parallel to AC. Great stuff. Okay, guys. I think you can see, right, why grade 9 was very important and why do we apply it here. So these are some of the things that you're going to need in terms of solving the riders. Okay, no, let me I also wanted you to go through these ones, right? But I'll just leave this as a nice exercise that you can try to do on your own, right? But you would see there that things like this angle here is equal to that. Why are those angles equal? Can someone maybe quickly tell me the reason?
Corresponding angles.
Corresponding angles, and there are more corresponding angles there. There is also which one and which one?
T, R, S, and RQP.
Right, TRS and RQP. Yes, these ones. Those are your other corresponding angles. There are other corresponding angles there, guys. Here I'm mentioning the issue of corresponding angles. There are also alternating angles, guys. In fact, there's a lot of angles there. Can you maybe quickly just identify those?
PSR.
PSR.
I'm not talking.
Mm-hmm.
PRS.
PRS. This one.
Yes. Is alternate to QPR.
Aha. Alternating angles. That's great. That's great.
So
Mm-hmm.
then we have WTS corresponds with TRP.
WTS corresponds with TRP.
Yes, sir.
Ah, that's very true. That's very, very true. Which other ones?
P is equals to
QRP. This one.
Yes. Corresponds to WTS.
Aha. So you're saying it's equal to this one.
Corresponds. I see. RTS.
You are doubting yourself, man. But it's true though. These are equal. Check. If I do this, can I not form an F shape? Look at it. You see? Every time you're unsure, always make sure. For corresponding, try to see if there's no F shape. But
So-
those ones,
Didn't we say that one WTS is equals to TRP?
yeah. So you can see, oh, the ones you chose, ma'am, they're outside those two.
Yeah.
Okay, yeah.
Okay. I'm saying
Uh-huh.
QRP corresponds to STR.
STR. Now that will be okay now. Because if you make your F shape, they are inside. Right? Both of them. Okay. Good stuff. So many more, guys. That is very much good. This one is what was asked in Gauteng. Yeah, guys, when you're looking at question 10, right, which maybe angles, fun angles can you identify?
Sir,
Mm-hmm.
angle PQB.
PQB, this one.
Yes.
Mm.
Plus angle DBQ.
Mm.
Add up to 180 degrees.
So angle Q plus angle B2 equals to 180 degrees. Those are your what?
Co-interior angles.
Those are co-interior angles. Okay. What else?
BDQ.
BDQ. Let's check that one. BDQ. This one?
Yes, alternates with PQD.
PQD. This one here.
Yes,
what a very nice observation there. Very nice one. So PQD, right, is saying it's equal to angle D. This because these are what? Alternating angles. Right. Mm-hmm.
Angle PQB.
PQB. Mm-hmm.
Yes. Corresponds to angle DBC.
This one.
Yes.
I hope you said this one. So
Yes, I did.
yes, angle Q is equal to angle B1, isn't it? Those are our corresponding angles. You can see they do make an F shape and both are inside the F shape there in that case. So those are your corresponding angles because DB is parallel to PQ. Right. Yeah, I think there are others. there's just this one that I see there that I see can be actually of great importance to the question. Is anyone who is recognizing it like I'm doing?
Which one?
Check properly. Open your eyes. Can you see it there?
Is it the one for F or the one for N or the one for U?
Ma'am, you want a clue? Okay, I'll give you a clue. It's the one for F. Mm-hmm. The one for F. Okay guys, this is the angle I was talking about. Look at angle P and then look at angle BTC, right? Those angles there, they are actually corresponding angles. They are your corresponding angles. Okay, I hope we got that. Okay, last one, I promise. Last one. Last one, guys. Let's see. I'm telling you guys, this is like the last one. Check. You see, when I say I promise, when a boy says I promise, they mean it, ne? So look at question 10. I just need you to give me at least three that you are seeing. 3 pairs though. Yes, Miss Vanessa.
Only 3, Nese.
Only 3.
Okay. I see angle CAB.
CAB, this one?
Yes. Plus angle ABF.
Plus angle AVF. What type of angles are those?
Co-interior angles.
Co-interior. Okay. First pair done.
Another one. Angle ACB.
ACB. Oh, here they made a mistake. Ne? It's actually a D there. Okay. ACB, which is this one.
No. ACB.
Yeah. ACB. Sorry. ACB. This one, yes.
Yeah, ACB is equals to CBF.
CBF. Okay, nice.
And then angle CAB.
CAB. This one.
Yes, one. And then Yana is equals to FBE.
FBE. Oh, that is very nice. What type of angles are those?
The first one that I've mentioned is co-interior, and the second one was alternating angles, and the third one was corresponding angles.
Corresponding angles, that's perfect. And then this side, I think I just need only one.
Okay, it's CDE. Is equals to HED.
It's equal to this one.
Yeah.
What type of angles?
It's plus, not equals to. Yes.
Oh, so you're saying CDE plus
HED.
It's equal to 1/8.
Yes.
Your reason?
Co-interior angles because DC is parallel to EH.
Okay. But here also, there's this one that is fundamental to the question, right? Can you realize, or can you identify it?
Where?
Check it. Like here, or rather, there are only two pairs there, by the way. So which other pair is missing?
Another pair. Kim DCE. Is equals to HEC.
Is equal to HEC. Nice. This was a crucial pair. Right. What type of angles are those?
It's alternating angles.
Alternating angles. Okay. All right. I forgot to say pinky promise. Good people, I pinky promise this is the last one. You see, this one is the last one. I should have said pinky promise. I'm very, very sorry for that. Okay, pinky promise is the last one. Give me a pair here on the first one.
Sir, ATC plus ECD. I say ADC plus ECD is 1/8.
Co-interior.
Yes, sir. Then B2 is equals to D3 alternating. Then D2 is equals to B3 alternating.
I will agree with D2 and B3, but B2 and D3, are they alternating? Do they make a Z shape? They do.
D, man.
Remember you said B2 and D3.
Yeah.
Remember?
Yes, sir.
So they do make a Z shape, isn't it?
Mm.
But now is line CD parallel to line AB?
Nope. Oh, okay. B3 and D2.
B3 and D2. Okay. Oh, said this, that B3 and D2. Okay. And then
D2 is parallel to B3. D3.
okay, all right. Okay, just the last one there would be these corresponding at these core interior angles. Okay, when you add them, you get 180. All right, and then this side, no, think we are good. I think we're good. There we can realize many of them. This corresponds with this, right? And then you have some other corresponding is this one and this one. Yes, ma'am.
So back to question 8. Out of order. B2 is equals to A because angles opposite equals A.
Yeah, that's true. That's true. That's true. That's true.
That's
B2.
called
Yeah, that's true. Angles opposite equal sides.
I'm practicing over.
Yeah, which is a very, very good thing, ma'am. We need that. Okay. And then it means even here you can tell that since FQ is actually equal to QD radi, then it should tell you that here D2 and F2 are equal and both should be X if ever they ask you one. So it's good to always identify that. Right. Other pairs, guys, you see, if I identify these two as corresponding, then you must understand that also this one would be corresponding with this one, right? It's still an F shape. It's still, still an F shape. It's like this one and that one. Good. Right, no, we are done with those guys. I said pinky promise, right? So it means I stick to my word. Right, so that was your grade 9. As you can see, there were quite a lot of them, right? The reason why we had to go through this hard and difficult process is because we need to train our minds to always identify those fun angles when we are given problems. It will assist us in similarity. It's not only about this, it will assist us in similarity, proportionality, and solving riders. Now, another part we need to know, right, is the grade 10 properties of quadrilaterals. And let's understand, guys, we don't really have much time. So the question I asked myself when I was making this is that, what's the main idea in terms of properties of quadrilaterals? Because we cannot start by saying, guys, this is how we prove this is a parallelogram, what, right? It's quite a lot of things that we're dealing with in grade 10. We are going to focus only on the main idea. The main idea is to know the properties of quadrilaterals. Is it possible for us at this moment to grasp all the properties? It's very much possible. Let's see. You just need to know this one shape, a parallelogram. If you know a parallelogram, then you are done with the rest. What are the properties of a parallelogram that we remember, guys?
Opposite lines are parallel.
Opposite lines. The opposite.
So let's do that one. Diagonals bisect.
But you were there. Okay. You've actually said the one that I felt like is the most crucial one at this point. The fact that the diagonals of a parallelogram bisect each other, good people, that is a very, very powerful property of parallelograms that is going to haunt you if you do not know it. So you must always know that here where the diagonals meet, these diagonals are bisecting each other. Remember, bisect is to cut into two equal parts. It means this line here will be equal to this one, and then this one here, which is this part, would be equal to this line here. Great. And then what other properties do we have? By the way, knowing the property will also allow you to prove the type of quadrilateral. Because if I say to me, prove that this quadrilateral is a parallelogram, you'd just have to prove that the diagonals bisect each other. Then you have proved that it's a parallelogram.
Sir, opposite angles add up to 180.
The opposite angles of a parallelogram are equal. Okay? Yes, they are equal. Good. They are equal. So it means this one here would be equal to this one. Good stuff. And then B will be equal to D. What other properties?
Opposite sides are parallel.
Opposite sides are parallel, which means AD is parallel to BC. And that tells you a lot of things, eh? You know, it means you have your fun angles. And then AB is parallel to CD.
Opposite sides are also equal.
The opposite sides are also equal, which means this side here would be equal to this side, and then this side here would be equal to that side. Good. Guys, we know a parallelogram. So if you know a parallelogram, I need you to then know, how does a parallelogram relate to the all other quadrilaterals? Remember, if your parallelogram, right, it so happens to have one of the angles inside it being equal to 90 degrees, then that automatically makes that parallelogram a rectangle. You understand me? So everything would still be pretty much the same. Right, the sides are going to be parallel to each other, but you're going to have one interior angle, right, one interior angle being equal to 90 degrees. Then you would have made that thing a rectangle. It's no more a parallelogram. Which means here, if one of the angles suddenly becomes 90 degrees, how can this angle become 90 degrees? You would have to squash this thing. I think when I was going through the shapes there was this, let me see, was this nice tool. Let me see, check this parallelogram. Here's a parallelogram, right? If I squash it, right, obviously, if I squash it and squash it, you can see that this angle here, I want you to take note of the angle at the corner. Of the angle at the corner, please take note of it. You can see that it's becoming more and more 90 degrees, and if you do that, you are forming a rectangle. So a rectangle is essentially a parallelogram with one interior angle be equal to 90. But now, in terms of a rectangle, the diagonals, right, here would be the diagonals, here would be the diagonals, and then here would be your other diagonal. They bisect each other, isn't it? They do bisect each other, right? Yeah, so that would be, so a parallelogram is just a rectangle is a parallelogram with one angle be equal to 90 degrees. And then how can you make a parallelogram become a rhombus? Well, you can make it to become a rhombus if the sides of that parallelogram, all of them are equal. So this one here, it is a parallelogram, but with having all sides being equal, then that means that becomes a rhombus, okay? And one of the nice special properties about a rhombus, remember, is that also by diagonals bisect each other, but I think you should have a 90-degree there, right? You should have a 90-degree there. So you've made it a rhombus. So what is important here, what I want you to take home, is that if I know the properties of a parallelogram, then I know the other shapes, all of them, because I know that a rhombus will just still be a parallelogram but with all sides equal. Rectangle will still be a parallelogram but with an interior angle being equal to 90 degrees. This one, what is special about it is that all the sides are equal. All sides are equal, right? Then what would be a square? A square would still be a parallelogram with equal sides, but at the same time with one interior angle being equal to 90 degrees. So a square combines this one and that one, then you form a square, you see. So everything comes from a parallelogram. Good. Then obviously there are other shapes that we should know, like a trapezium. A trapezium is nothing special. One property about it is that one pair of sides are parallel, eh? One pair of opposite sides are parallel, right? This is a good background to know. And then a kite, the adjacent sides are equal, eh? That is one special property about a kite, is that the adjacent sides are equal, and the longer diagonal bisects the other one. Yeah, good. Again, a bit of practice, but here what did I want us to achieve? So here, right, here what was happening? Oh yes, now I was showing you this one because now look at the instruction. It says A, B, C, D is a what? Is a parallelogram. The moment we see that statement, I want us to remember that you are going to look at A, B, C, and D. Then ensure that you remember that this side will be equal to that side, and then this one would be equal to that one. And remember that they would be parallel, right? Remember that they would be parallel, like that. But also what is very important is that inside there will be diagonals. So AC is a diagonal and they meet at M. DB is also a diagonal. So please know that MD would be equal to MB. Your reason would be diagonals of a palm. Okay, to say diagonals of a parallelogram. So it means this side here should be equal to that side. And then another one that you should then realize there is that AM, right, is equal to MC, right? AM is equal to MC. Remember, you are going to say diagonals, diagonals of a palm, right? Very nice. Another one here says that ABCD is a parallelogram, right? So immediately remember the properties related to what? To a parallelogram. But the nice thing about this one is that we don't have diagonals, so we are we are okay. But remember, a parallelogram also brings up the fan angles. That is also an important thing about a parallelogram. It brings up the fan angles, meaning that you can now say this angle is equal to that, this one is equal to that. Okay, so and then also this B is equal to this angle there, alternating angles. So now you'll now be linking these things. Okay, and it's very important because with that you'll be able to prove similarity with ease. Oh boy. Right. And then the last one, like I am saying, it's the last one in terms of these things. So here also the question says ABCD is a parallelogram. Now you do immediately, I want you to always look at the diagonals. BD is a diagonal, which means this side must be equal to that. And then CF must be equal to what? To AF. And then these sides must be parallel. And then these ones must be parallel and equal again. Right? That is how you would be able to realize that. And then that is why now you see these questions such as show that E is a midpoint of AD. If you cannot recognize the properties of a parallelogram, you are doomed. I'm sorry to say that, but you are very much doomed, because to prove that E is a midpoint, actually you would have to start by saying AF is equal to FC, and then you tell them FE is parallel to CD. Then because of that, it will mean that AE is equal to ED. Then you tell them this is the converse of the midpoint theorem. But we are still going to go through that. My thing with you is that I want you to recognize the tools that you must use whenever you approach any question in Euclid. And so far we have talked about the fun angles, and now I'm telling you about the properties of a parallelogram along with other quadrilaterals. If you have those tools, you will solve problems with ease. You understand me? And you see here, prove that PQ is equal to FE. You would have to prove that maybe the corresponding angles or PQ are equal and the likes. But those ones, we'll talk about them. Right. Good. Then coming here, the grade 11 9 theorems, right, which is 9 of them. So usually what I do is that I group them into 3. I group them into theorems that are talking about a center, and then theorems that are talking about cyclic quads, and then theorems that are talking about a tangent. If you are able to group them like that, believe me guys, you will be okay. So first of all, talking about a center. Now when we're talking about a center, right, here are your 3 theorems that are talking about a center. The first one says that an angle subtended by a chord at the center is equal to 2 times the angle subtended by the same chord at the circumference. So what does this mean? This means that the one here at the center, the one here at the center, right, would be 2 times the one at the circumference. And then this theorem has 2 other sister versions. The first one is this one, to say still this is the angle at the center, so you should say it's 2x. It's double the one subtended at the circumference. By the way, good people, another way to master Euclidean geometry is that you just always go to 2 points on the circumference. Then using your fingers, right, touch those 2 points and then follow where they are going. Follow where they are what? Where they are going. They will always give you an angle. If they don't give you an angle, it means that you don't have to worry about those points. But always do that. Follow them and see. If they give you an angle, for example, they form 2x, right? It's where is it formed? It's formed at the center. Then you move from the very same 2 points, then follow where they are going. Where are we going now? We are going to the circumference, and we are forming another angle at the circumference. So the angle formed at the center will be twice the one that is formed at the circumference. Same thing here. Move from 2 points. This is your first point and your second one. Move to the center. Look at the angle that they form at the center. Then move from the very same 2 points, right, and go to the circumference now. They form this angle. Then you must know that that one that is formed at the circumference is going to be half of the one formed at the center, which means the one at the center is double the one at the circumference. Good. And then even here, right, this is a point, this is a point. Move to the center, those 2 points though, when it's like this, good people, when it forms a smaller nyana shape, quadrilateral shape, what I need you to remember is that the one that we're talking about that is formed at the center is the one that is outside. And then this one that is outside will be double the one that is formed inside. Okay, so when it's looking like this, I need you to remember that we're talking about the one that is formed outside. It's going to be double the one at the circumference. Good, I hope you're fine there. And then here, right, we proved this one. If you can remember, this one we proved it yesterday. We also proved this one. Line from center perpendicular to chord. So if you do have a line from the center and that line is perpendicular to a chord, you can conclude to say that this line will be bisecting the chord. Okay, so it means we'd say this line should be equal to that. And then here, if you have a diameter, right, if you have a diameter, just move from the 2 points of that diameter, go to the circumference. The angle formed by those 2 points to the circumference of a diameter, that angle will be 90 degrees. And your reason will be angle in a half circle. This is a nice way to visualize them. Euclidean geometry is all about a condition and then a conclusion. So what we're saying is that for those that are talking about a center, here are the conditions here. The first condition is that if O is a center, then your conclusion will be to say, therefore BOC should be 2 times angle A. And then your reason should be because the angle formed at the center should be equal to 2 times the one formed at the circumference. So whenever you have this condition, you conclude this. Right. And then here, when you have this condition again that O is a center, and then you find that you have a line from the center to the chord, right? So if you find that OC is perpendicular to AB, those are the 2 conditions. O must be a center and OC must be perpendicular to AB. If that is the case, you conclude to say AC will be equal to BC. What is your reason? Because you have a line from the center that is perpendicular to the chord. So this is the conclusion part. This is the conditions part. The condition should be this type of sketch. Same thing here, right? If you happen to have O as a center and then AB is a diameter, that is a 2 conditions, right? You conclude to say that angle C should be what? Should be 90 degrees. Your reason will be angle in a half circle. Right. That is what we have there. So the conditions are here. The conditions are a sketch like this. And then the conclusions will be like this. I hope we got there. Any questions so far? All right. And then how do converses work then? If we know in terms of this, right, then how does a converse work? Well, a converse is the reverse in this sense. On a converse, you are given the theorem. And then when you're going to conclude that the theorem is only true if the condition is met by adding the word converse. Guys, you see what I said here, even I myself, I don't understand what I'm saying. But don't worry. I think through looking at it, we should understand. So, what I'm saying is this. For a converse, you are given, remember at this slide, we said this is the conclusion you make because you have a center there and you have a chord subtending an angle at the center and the very same chord subtending an angle at the circumference. So, you conclude to say the angle that is formed at the center is double the one at the circumference. For a converse, you are given this one as the condition. And then when you conclude these, all of these that were the conditions, those are now going to be your conclusions. These ones are now going to be the conditions. That's English, yeah? So check. we are already being given the conclusion here to say this angle at the center is twice the one at the circumference. We are already being given that. You might be given that, or you might prove it that actually the one at the center is double the one at the circumference. If you happen to prove it, or you happen to be given, your conclusion will be to say O must be a center. Why? Because this is only true if O is a what? Is a center. So the converse, this is how they work. A question will be like, prove that O is a center of a circle, given that BOC is 2 times angle A. Your job will be to say, since BOC is already twice angle A, then O must be a what? A center. Then you just add the word converse before you say the theorem. You just say converse angle at center equal to 2 times its circumference. What you are simply saying is that this can only be true if O is a center. Of which, on the previous slide, this was the condition. You had to have a center for this to be true, for you to conclude this. But for a converse, you are given the conclusion. You are given the conclusion as a condition, right? You are given the conclusion as a condition when you are giving them the previous condition as a conclusion. So I don't want to speak English a lot, good people, right? What we must just understand is that if you are given that this is already twice that, it can only be true if O is a center, your reason will be converse. Same thing here. I want you to look at this diagram because they like it a lot, right? You are given something like this. You are already given that AC is equal to CB, and of which you have a line from the center to a chord. AC can only be equal to CB if OBC or OCB is a 90-degree angle. If OBC is a 90-degree angle. You understand me? So why? Because of the converse of a line from center perpendicular to a chord. So you are moving from this, concluding that to say it must be 90 degrees there. Right. The type of angles, the type of questions will be like, what is the size of OCB? You will tell them OCB is 90 degrees because of the converse. And you say this is because AC is equal to CB already. Oh, but what I was supposed to prove, you are already giving me it. So it should mean that OCB is 90 degree. Hey, a lot of English here. So let me actually maybe remove these things. They might be a bit confusing. So what I was saying here, guys, is that if ever the situation is like this, you conclude to say this O is a center, then you just use converse. If the situation is like this, you just conclude to say that OCB is 90 degrees and your reason will be converse. You won't say line from center perpendicular to chord because OC is not given that it's perpendicular to AB. So you use converse instead to say that OCB must be 90 degrees. And questions that will be asked in terms of that are questions like prove that AC is equals to CB. No, it's not those ones. It's not those ones. It's to say prove that OCB is 90 degrees. When you would tell them it's 90 because AC is equal to CB already. The chord is already bisected. And then if you so happen to find this situation here whereby you have a 90 degree already, then you conclude to say that AB is a diameter. Okay, you conclude to say since the angle C is already 90 degrees, then AB must be a diameter because it's only true if AB is a what? Is a diameter. Then we just use converse. That is how a converse works. It's you being given this part and then using it's you being given this one instead of being given a situation like this. So it's to be given the conclusion in a way. Right. And then second part about quadrilaterals, I also told you that I group them into three. So I usually just group them into the following. So let's see. The condition is that if ABCD is a cyclic quad, if ABCD is a cyclic quad, then you're going to conclude that angle A plus angle D will be 180 degrees. You will say opposite angles of a cyclic quad as your reason, and then you will conclude that angle B plus angle C will be what? 180 degrees, opposite angles of a cyclic quad, because ABCD is a what? A cyclic quad. Also here, if you are given that ABCD is a cyclic quad, you can conclude to say an exterior angle of a cyclic quad is just an extended version of that cyclic quad. It's an extended line of that cyclic quad. I did try to show it with dotted lines because I know this is something that they don't show us in our textbook, but you can have an exterior angle in all these different directions. So B1, if it's your exterior angle, it's going to be equal to the interior opposite. Okay, so it's going to be equal to angle D. That is what you're going to conclude. By the way, good people, which other exterior angles can we... Okay, I didn't give them names. I'll just say this is C1. C1 is going to be equal to the interior opposite. So it's going to be equal to angle A. Okay, C1 will be equal to angle A. What's your reason? Exterior angle of your cyclic quad. Right, then you can have many others, right? I'll just show one with maybe a white color. I'll just show you this one. Angle D would be equal to which angle, guys? Can you tell me which angle is equal to that? Let's call it D1. Angle D1 will be equal to which angle?
ABC.
Will be equal to angle ABC. Perfect. ABC, the interior opposite. Okay, so interior, when I say interior opposite, I mean the one next to that angle and then the one opposite to that angle. So that will be the one equal to the exterior angle there. ABC, exterior angle of your cyclic quad. Great. And then lastly, in terms of these ones, right, it will be these ones that have what you call, if I put some diagonals of that cyclic quad, that diagonal is going to be making some angles. So you can have many pairs of angles that are equal there, for example, but you must know that this is because ABCD will be a cyclic quad. So A1 is equal to B2. A1 is equal to B2 at the corner there, right? Hit this one here. They are equal because those are angles in the same segment. And then A2 is going to be equal to... sorry. A1 is equal to B2, which is the orange part. A1 is equal to B2, right? And in terms of that one, right? We must be very, very careful because it pops out a lot. So let me try to say, oh, doesn't want me to, okay, let me do this. So in terms of this, right, we must be very, very careful. Like I said to you guys, Euclidean geometry is all about moving from 2 points of the circumference and following where they are going. So if I move from D and C and follow where those points are going, they form an angle D1 at this part of the circumference. And then if I move from the very same angles again, then I move to where they are going, they form B2 at another part of the circumference. So because of that, we say A1 and B2 will be equal. Your reason, you say because these are angles in the same segment. Let's see again. If I move from A and D, I follow where it is going, it forms ACD, right, which is C1. And then if I move from the very same point, I go to the other part of the circumference, they form A1, a B1. So that means B1 should be equal to C1. What is our reason? Angles in the same segment. Okay, look at these points B and C. If you move to the part of the circumference, they form A2, and then again they also form D2. So because those two angles are going to be equal, right, and your reason will be angles in the same segment. So please, all the time, just move from 2 points and follow where they are going. It will lead you to the right answer. Right, and then what would be the converse is there in terms of that? The converse would be that you are already given the following. You are given the conclusion. So when you are going to take it as the condition, and then you are going to conclude using this one. So if this is the condition, this will be the conclusion. So if already you see that you are given angle B and angle C, right? And when you add them, you find that it's 120 degrees. Your conclusion will be to say that is only possible if ABCD is a what? Is a cyclic quad. That will be your conclusion. So it's like you are given the right hand side, and then you conclude with the left hand side. And then same thing here. If you find that this angle formed here is equal to the angle formed there, right? Either you proved it or you are given, then it means that your conclusion will be it's only possible if ABCD is a what? Is a cyclic quad. That is why questions come and say that prove that what is a cyclic quad. This is how you prove them. You prove that maybe the opposite sides add up to 180 degrees, or you can prove that the angles in the same segment are equal. If you can prove it, it means that thing is actually a cyclic quad. Okay. And then lastly, it's about tangents, right? Tangents, there are also 3. And then the first one is that if you find that OB is a radius and AC is a tangent, you conclude to say OBC must be equal to 90 degrees. Your reason will be tan perpendicular to right. Okay, so you would conclude to say here it's 90 degrees. Oh, it's 90 degrees. Then you say tan perpendicular to right. Then here, right, tan chord, right, we proved it yesterday. If you find that KR is a tangent, right, and then there is a chord, good people, all I need you to do is to look at the angle between the tangent, which is KR, and the chord. The angle that is between there is what? It's K1. Now I need you to move from 2 points of that chord and then follow where it takes you. Where it takes you will be the angle that is equal to K1. That angle is called the angle in the alternate segment. So it's all about identifying the chord and then moving to the circumference to the angle formed by that chord. That will be equal to the one in between here. So that means we can even have K3, and then I move from these 2 points of this chord, right? Where it takes me is going to be the angle equal to K3. I hope that is clear. So you say K1 equal to H1, angle H, and tan chord theorem. Then if tangents are from the same point, meaning AB and BC, if they are tangents, right, you conclude to say AB must be equal to BC. So you conclude to say AB must be equal to BC because these are tangents from the same point. Ooh, and then I know someone will then tell me that, oh, this means these angles are equal, which is perfect. Good people, those are the theorems in grade 11. I hope you understand them. It's only 9 of them, so I group them so that you don't, really struggle that much. All you have to remember for me is that the one for a center is 3 of them. Angle at the center is equal to 2 times at the circumference. Line from center perpendicular to chord. So you can even draw them to remind you, right? Line from center perpendicular to chord, right? And then angle in the same segment, that will be this one here. And then cyclic quad, opposite angles of a cyclic quad. So you must have a cyclic quad, opposite angles add up to 180 degrees. And then exterior angle of a cyclic quad, if you have a cyclic quad, the exterior angle will be equal to the interior opposite. And then angles in the same segment will mean that if I have something like this, there's something like that, this angle will be equal to that, this one will be equal to that. Okay. Then lastly, about tangents, right? There are also three. Remember, tan perpendicular to right will mean you have a tangent, you have a radius, in between you conclude to say it's 90 degrees. And then tan perpendicular to chord means you have a tangent, you have a chord. The angle between the tangent and the chord will be equal to the angle formed by the chord at the circumference. And then tans from the same point, that is the easiest one, whereby you just look at the tangents from the same point, you conclude that they are equal. Those are your 9 theorems. I hope that is good there, right? I hope that we remember them. Now it's time to actually work on these, right? God knows the time I took to get here, but trust me, it was very much worth it. So now here I'm going to show you how do you approach the problems, right? So that you always get your marks. So you start on the instruction. The instruction is going to give you the following. When you look at the instruction, I need you to use it as a tool. Instruction, use it as a tool to get where you are working, where you are going to get your angles. Can I find a better ways of putting this? Your instruction is going to give you it's going to give you, right, whether you are working with, maybe showing it is much better, whether you are working with theorems related to a tangent, or whether you are working with theorems related to cyclic quads, or whether you are working with theorems related to a center, or whether you are working with theorems or whether you are working with fan angles. That is how you are going to use your instruction. It's a tool to tell you whether you are working with angles that are dealing with the center, theorems that are dealing with the center, or theorems that are dealing with cyclic quads, right, or theorems that are dealing with tangents, thereby leading you to correct answers, or whether you are dealing with theorems related to fan. So how will you know? If they mention something like a center O, then you know that already I'm working with theorems related to a center. If they mentioned that it's a cyclic quad, or sometimes they won't mention it, if you can just locate 4 points on the circumference, then already know that theorems about a cyclic quad apply. For example, look at this one. If you can check, they said RDS is a tangent to a circle O at D. If BC equal to DC and CDS is 40, calculate with reasons. Where did they mention anything about a cyclic quad? They did not. I bet they did not. But you must know that as long as I have 4 points on the circumference, 1, 2, 3, 4, that is actually a cyclic quad. So they don't have to tell you all the time. In fact, they are not going to tell you. Please, guys, always remember that if you have 4 points on the circumference, you can use theorems related to a cyclic quad. It means you can already say angle A plus angle C should give you what? 180 degrees. And then if they mention the word tangents, then definitely you know that you are going to remember theorems related to a tangent. This one is going to apply if they tell you that there are parallel lines. If they mention the parallel lines, then you know that I'm going to have to identify some of the fan angles. I think we spent most of the time doing that. So in this case, check, they said RDS is a tangent. You start there to say, if RDS is a tangent, I have only 3 theorems that are talking about tangents. The first one says that if I have a radius and a tangent, the angle in between is 90 degrees. And indeed, OD is a radius. So that means already I know that here is what? It's 90 degrees here. It's 90 degrees because of tan perpendicular to radius. And then the second theorem that I have is that the angle between a tangent and a chord is equal to the one in the alternate segment. Here is a tangent, here is a chord. A chord, I have chord AD, right? Now, remember guys, you just move from the 2 points to the circumference and you check the angle formed by that chord. That angle here would be equal to the one between the chord and the tangent. Then you can even check others. Look, they said D1 is 40 degrees, right? D1 is 40 degrees. And then the chord there is DC, because it's the angle between the tangent and the chord DC. So what are you going to do? You are going to say D1 must be equal to, look, you just have to locate the 2 points of the chord, then you follow where they are taking you, the angle formed at the circumference. You see which angle is it? It's B1. So it means here it should also be what? Be 40 degrees. That's what you do. And then there's, I don't remember who, guys, there's someone who was always telling me about the angles opposite equal sides. Are you there or are you not there? Chichi, are you sleeping?
I'm right here.
Oh, okay. Good. So B1 will be equal to which angle, ma'am?
B1 will be equal to D2.
Would be equal to D2. Perfect. And both will be 40 degrees. Angles opposite equal sides. Now, well, there is another chord again. Look at the angle between the tangent RDS and the chord DB, right? Then check the angle formed by DB at the circumference. It should tell you that this angle, this whole angle BDS, should be equal to this angle A. Alright, okay. But sometimes you don't need all of the theorems, you just need specific ones in a way. You must just identify them strategically. By the way, you have a center. They said circle O. That already gives you a what? A center. It means you must also remember theorems related to a center. Right? You must also remember theorems that are related to a center. So those theorems, remember, they are only 3. Angle at the center is twice the one at the circumference. Does it apply here? You check. If I move here and then I go to the center, BD is subtending an angle at the center, which is O1. And then if I move from the very same 2 points, I go to the circumference, O1 will be double of this angle. It tells you that if this is x, O1 will be what? Will be 2x. Already you know that. Good. And then, by the way, that theorem, also remember that other ugly version of that theorem, this one here. It tells you that if you can have another angle here, if this is 4y, it means this angle here will be y. Oh, sorry. If this is 2y, this angle here will be y. Okay, because the one at the center is twice the one at the circumference. I'm using a different letter because if I say 2x, I'm now saying that O1 is equal to that DOB, which is not true. But it's just something to take note of. Then you go to your questions, right? Your question starts by saying that find the angle BDC. Where is BDC, right? I know we've made a mess here. BDC. So BDC is this whole angle here. So I'm gonna try and remove everything, right? And just try to work on a clean slate. That was just to show you how you can identify the theorems, right? And how the questions guide us. So we're looking for BDC here. Here's BDC, that angle. It's equal to which one? We already know that it's going to be equal to angle A, right? We already know that. Yes, ma'am?
Isn't that the angle that you highlighted? Isn't that BDS?
Good. I wanted to check whether you're not sleeping. That's good. You're not sleeping, guys. Perfect. Perfect. BDC is this one, right? Is this one. That is the one, BDC. So that angle, how can we find it, right? Remember, we already had said that this one should be 40 degrees. So we must tell the examiner first of all, right? We must tell the examiner that for that 7.2.1, right? Angle D1 is equal to angle B1. Both are equal to 40 degrees. Why? Remember, that will be your tan chord theorem. And then now that you know this is 40 degrees, then you say angle B1 will be equal to your BDC, and both will be 40 degrees. Why? Remember, these are angles opposite, equal sides. Perfect. Then you're good. Right, so you know that this will also be what? That would be 40 degrees there. Right. And then 7.2.2 then says that find angle C. How? So angle C is this pink one, right? We must start here by saying B1 plus angle D2 plus your angle C. They give you what? 180 degrees. And you tell the examiner this is because of sum of angles in a what? In a triangle. So since B1 is 40 degrees and then D2 is also 40 degrees, then you are looking for C. So your C will be 100 degrees. Okay, and whatever you get, please put it on your diagram. You are going to have a diagram sheet, right? Make sure you put it on the diagram. Then they want what? Angle A. How does angle A relate to angle C? Can someone tell me there?
They add up to 180.
Angle A plus angle C add up to 180 degrees. What is your reason?
Opposite angles of a cyclic quad.
Opposite angles of a cyclic quad. Right. You can see that A, B, C, D, we did say because it's 4 points on a circumference, it means it's a cyclic quad. So the properties of a cyclic quad apply. So we say angle A plus 100 degrees will give us we'll get our angle A. So therefore angle A will be equal to what? 80 degrees. And once you get it, make sure you put it there, 80 degrees. Then the last question needed angle O1. How can we get angle O1, guys?
We say O1 is equals to 2 times angle A. Then your reason angle at center is equals to 2 times angle at circumference.
Perfect, perfect. Now we are identifying our theorems. Now we don't have O1, but we do know that A is 80 degrees. So therefore that should mean that O1 is 160 degrees. Beautiful. Beautiful. But I want to challenge you guys. I cannot just say I'll give you something this easy. No. How would you get angle B2? I want to give you exactly 3 minutes to get angle B2. But now, yes?
So B2 is 10 degrees.
It's how much?
10 degrees.
10 degrees.
Yes, sir.
How do we know it's 10? What's your reason?
We firstly have to write that OB is equals to OD. Our reason is both radii. Yeah. B, we say B2 is equals to D3. Angles of angles opposite equal sides. Okay. Because O1 is 160. 101 plus B2 plus D3 is 180. It's going to be sum of angles in a triangle. Okay. It will be same 160 plus 2B2 is equals to 180. Then we solve for BT and we get B2, we get that it's 10.
Perfect. That is marvelous. Wow. If I was in the class, I'll say clap hands for that lady. That's very nice. But there are emojis there, guys. Oh, okay. Right. No, that's very nice. Brilliant. So B2 is 10. Sure, I thought I made it difficult. Wait. I'm not. Okay. Okay. All right. Okay, Shaf, let's move to the next one. That's very good, guys. Well done. Right, let's look at this one here, right? Now let's make it interesting by having 2 circles now. Name with reasons 3 other angles equal to x. Anyone who can assist us? The one you see, but do read the instruction first. The instruction said 2 circles have a common tangent. So you have a what? You have a tangent TAB. So TAB is your tangent there. I'm going to try and make it a bit more visible. TAB is our tangent there. Great. Or should we change color? Let's make it maybe pink, red, orange, red. Red is nice. Right. TAB is our tangent. And then let angle Q be x. So this one is x there. As you can see, this is x. So guys, can you tell me which other angles are equal to x? Check it. Remember properties related to a tangent.
Sir.
Yes, ma'am.
I think A2 is equals to x.
A2 is equal to x. Let me check that one. A2, this one is equal to x. What's your reason, ma'am?
Tan-Chord theorem.
A2 is equal to angle Q, but please do indicate it's equal to Q first, then you say x. Tan-Chord theorem. That's perfect. That's true, right? Because if we can check there, this is our chord here, and then it forms an angle at the circumference, which will be Q there. Okay, right. Any other? I saw a hand, Miss Masupe. Yeah.
I was going to say what she said.
But you know what is the nice thing? They wanted 2 more. So which ones are 2 more?
Give me a second.
Which ones?
Sir,
Mm-hmm.
A5 is equals to X. Opposite angles.
But we don't start there. You guys are cheating. A2 is equal to A5 first, isn't it? Right. So we say angle A2, right? Very good observation, guys. A2 is equal to angle 5. And both should be X though, because these are vertically opposite angles. Okay.
So,
Okay. Oh, that's not 9 point. Yes, ma'am.
I think the other one, A5 is equals to P2.
So because A5 is equal to A2,
Oh,
that would mean A5 is also equal to P2 there, because now remember it's a tangent and then there is a chord, and then the angle formed there is P2. Great stuff, great stuff. So we can therefore say angle A5 is going to be equal to angle P2, and both will be X. Tan chord theorem. Tan chord. Oh, by the way, you must write theorem, eh? Yeah. Great stuff. Then we got our 5 marks. But you know, those 5 marks, how they are usually distributed, right? Because yeah, it can be marked for a reason, and then a statement, and other parts they will just mark a statement only. For example, you see it's tan chord, so they might just mark maybe just a statement. All right, so I can also put X there, right? I can say therefore this is X, this is also X, and then this is also X. Great stuff. The 9.2.2 says prove that APTR. Where is APTR? Where is AP. Wow. TR. APTR. Okay, is a what? Is a cyclic quad. So it means we're talking about this one here. We need to prove that it is a cyclic quad. We give it a what? Black, blue. So how do we prove that, guys? Okay, nice bluish color there. Right. The moment the question says prove that something is a cyclic quadrilateral, you need to remember the properties of a what? Of a cyclic quad. Meaning you have to remember the 3 theorems of a cyclic quad. Remember there are only 3. The first one talks about opposite angles of a cyclic quad. The other one talks about the exterior angle of a cyclic quad. The other one talks about a what? Angles in the same segment. So from those 3, you just have to prove that either the opposite angles add up to 180, or prove that the exterior angle is actually equal to the interior, but then you'll use the word converse. Okay, so how do we do that, right? You check here which one you can be able to prove, right? And I know there seem to be quite a lot, and sometimes it can feel like there is just no solution to this, right? But there is a solution, right? Wait, is PT a tangent? They say they didn't tell us. Oh, yes. You see, they said PT is a tangent to the smaller circle, right? That is a very underrated statement, eh? So if PT is a tangent and look at TAB is a tangent, can we not say that this line would be equal to that line? What would be our reason if we say that? Do you still remember the reason?
Is it tangents from same point?
Yes, both of them are tangents from the same point. Great. Tangents from the same point. Good. And then now that we know that, what does it mean, right? The implication now is that P1 will be equal to, P1 would be equal to what? To A3, right? Why? Because we do know that those would be the angles opposite equal sides. Great. So those two angles are equal. So check, right? If maybe we can prove, right, that a P1, check, if you can prove that maybe P1 is equal to R2, then you would have proved that the exterior angle of a cyclic quad is equal to the interior opposite. And then from there you could say that therefore it's a cyclic quad, right? So, or if you want, you could prove that R1 is equal to this one, right? Depending on which one you feel like you might be able to navigate through much more easier. Which one can be more easier there? Check it. I want to give you 2 minutes. No, just at least just 1 minute to look at it. Okay, so let's see. Remember we said P1 is equal to A3, right? One of the things that I myself have used, the tools that I've used to always be able to link two angles is this, right? For example, in this case, I need to prove that P1 is equal to R2. When you look at it, it will seem very impossible because you're looking very far. You understand me? You're looking far. This is what you must do. Look at P1, right? And then ask yourself, is P1 equal to any other angle here that we can say it's equal to this? Already we said it's equal to A3 only. That is fine. You are done with P1. Leave P1 alone. And we already wrote that P1 is equal to A3. Then I want you to go to R2. Ask yourself, you're going to be working in reverse. Ask yourself, which angle is equal to P2? You see these questions about name 3 other angles equal to X. It's a technique that they want you guys to use all the time so that you know how to tackle these proof type questions. What you do is that you want to prove that P1 is equal to R2, right? Look at R2, ask yourself which other angle is equal to R2. Are you able to identify that angle? Is there anyone who is able to see which angle is equal to R2?
Okay.
Which one is it?
Is A1 equals to R2?
A1 and R2. Is AQ equal to RQ? Oh, when they are not equal. Check for another one. I'll buy you a stock sweets, guys. You know, a lollipop, stumble lollipop. Just look for me an angle equal to R2 here. I know, I trust in you. Unlock that potential you have in your brain. I know you can see this. The answer is right in front of you. I know you can identify it. If you've forgotten, even go back to the instruction. Look at the instruction, what you have, and go back to the diagram. I trust in you guys. Someone must get this correct. Which angle is equal to R2?
Next to the A3 and A2.
A3 and A2. Remember, exterior angle of remember that PTRA is not a cyclic quad yet, because you know it's not in a circle. All the 4 points are not in the circle. This point is not in a circle, so we can't use properties of a cyclic quad. But we want to prove that indeed it is actually a cyclic quad, right? So we said one of the ways that if we can prove that R2 is equal to the interior opposite, it will mean that it's a cyclic quad. Yes, ma'am.
Is it A6?
That's A6. Oh, perfect. Very nice, ma'am. Congratulations. You've won yourself a nice, big, fat lollipop. R2 and R6 are equal. R2, check it. R2 is equal to what? To A6. What's our reason?
The exterior angle of a triangle.
Ma'am, I take my lollipop back. Tan chord, right? Tan chord theorem, because you can see TAB is a tangent, and then when you look at A and Q, right, which is the chord, it forms an angle R2 on the circumference. So R2 should be equal to A6. So where do we go from there? Now that we know that R2 is equal to A6. Now it's a chain. A6 is also equal to what? To A3, isn't it? What is the reason?
Vertically opposite.
Vertically opposite angles. For you to always identify vertically opposite angles, you just make an X where the angles are. You just make an X. Then if they are facing each other like this, then definitely it's vertically opposite angles. So we say vertically opposite angles. But check, A3 is equal to P1. A3 is also equal to A6. While A6 is also equal to R2. Then what does that tell you?
They are all equal.
Right. So therefore angle P1 is going to be equal to angle R2, right? You can say both are equal to A6. Or yeah, you can say both are equal to angle A6. Yes.
So you said, why is it that P1 is equals to A6?
P1 is equal to A6. Oh, okay. Remember, P1 is equal to A3. Check this part. P1 is equal to A3. Right? These P1 and A3 are one and the same thing. So I can actually write that this is P1 here. So R2 is equal to A6 and P1 is also equal to A6. So both of them will be equal. You get me?
Yes, sir.
Right. So because P1 is equal to R2, then we conclude to say, therefore, right, APTR is a what? A cyclic quad. Is a cyclic quad. Then your reason now will simply be, remember that this is an exterior angle of a cyclic quad. So you just put converse exterior angle of your cyclic quad. Then you have proved it. Okay. So this is what this is the other one. Let me see if we have time. Right, 3 minutes or so of solving this one. Check, good people. Right here we have a diagram. They say AC is a diameter of a circle. The fact that they said a diameter, right? The fact that they said a diameter AC, it means which theorem reminds us of that? We should be reminded of angle in a semicircle, isn't it? So it means this is 90 degrees there. Then they say now, and the fact that it's a diameter and O is a center, let's be reminded that it means OD is equal to OC and then it's equal to OA. I personally always make sure that if I have a center, I recognize the radii. Okay. And then now, because I would have recognized the radii, that should remind me now also that this angle should be equal to that angle there. Perfect. Then they said that OD join AE is perpendicular to BD. They said AE is perpendicular to BD. If AE is perpendicular to BD, that means here we have a what? We have a 90 degree. Which angle, or rather which theorem reminds us of this? We must be careful here. There is a theorem that says that if you have a line from the center and then that line is perpendicular to your what? A chord. Specifically, the line must be from the center, not from the circumference. So you would look at OE instead, right? You would look at OE, of which OE, yes, it can extend to A, which is literally the same line, but here's OE. And if I can actually prove that E3 is 90 degrees, what can I conclude? Remember, I can then conclude that DE will be equal to EB. So I must first ensure that I find the angle here, of which is going to be very easy to find since AEB is already 90 degrees. Before getting carried away, they said C is 33 degrees, right? So C is here, it's 33 degrees. Then they say calculate with resistance the size of angle A1. Would we be able to calculate A1? A1. Angle A1. It's at a very, very odd position, eh?
Yes, we can be able to calculate it.
Please
You know
assist me.
You see, reasoning, I'm still takaring. But
Okay.
B1 plus, angle B plus angle C plus angle A is equals to 180 degrees.
Like this
Angle
one.
A, and angle 2 and angle C.
So, so we can get A2, right?
Yes.
Okay. So if we say 180 minus 33 minus 90, so 90 minus 30.
And that's couple plus.
It's what? 90 minus 30, 60. So it's 57 degrees here, ne?
Yes.
Okay.
And then you said you want which one?
A1.
A1. Just a minute.
Yes, yes. B2, B2. Wow, ma'am, your minute. That was a very long minute. Okay, okay. um, guys, remember what I said. Do not look far too much. Look at A1, right? Look at A1 and then ask yourself, which other angle is equal to A1? Yes, it is this one, but there is another angle that is equal to A1. Who can tell me which other angle is equal to A1?
It's B1.
It's B1. Because if I move from D and C, I'm forming this angle at the circumference. And then if I move from the very same points to another part of the circumference, I'm forming B1. So it means A1 and B1 are equal. So check, if I can get B1, it means I got A1. How can I get B1?
Get B2.
B2. But wait, there's a 90 degree here. Do you see it? What can we do?
We say 180 minus 90 minus 57 is a B2.
Yes?
Can't we're gonna get E3 to be 90 degrees because angles on a straight line. Then we're gonna say 180 minus that 90 minus that 33 will give us B1 because of its angles in the sum of angles in a triangle.
Perfect. That is it. So for 7.1, you start by saying angle E3 should be equal to angle should be equal to AEB, right? And both will be 90 degrees because of sum of angles on a what? On a straight line. So when you add them, right, you will get 180. So that's why E3 should be 90. Then you say now angle E3 plus angle B1 plus angle C, you get what? 180 degrees. Why? This is because of sum of angles in a what? In a triangle. So E3 being 90, you do not have B1, but C being 33 degrees, you would be able to get what? You would be able to get B1. So you say 180 minus 90 minus that, you should get 57 apparently. Is it 57? Yeah, I don't know. It should be 57. 57? Yeah, I think it should be 57. So if B1 is 50,
Yes, it is.
it is perfect. If B1 is 57, then that's when you can say, but B1 is equal to angle A1. Why? Because these are angles in the same segment. Then you say, therefore, angle A1 should be 57 degrees. Good people, that is how we solve those. It's a very, very nice way of solving. The main thing here is to say, instead of you looking at the angle and trying to find it directly, move backwards like you're playing chess, right? Move backwards and then say, or like you're playing checkers. Move backwards, look at that angle that they want, and ask yourself which other angles are equal to that angle. Then after doing that, you will then see a chain of events that can lead you to solving the problem. Even D2 here, if I wanted D2 there, what can I say? I'm just gonna say, oh, remember now this is 57 degrees. I'm gonna say D2 is here. The one D2, right? I say, okay, D2 is equal to which other angle? In this case, when you look at D2, it's not equal to any of the angles, and we can't say C because it's not subtended by the same chord. So since D2 is not equal to any other angle, it's not a train smash because D2 is part of angle D, and we know that angle D is equal to what? Angle A1. So we could start there by saying what? Angle A1 is equal to angle D. Remember, these are angles opposite equal sides. This is because of the radii, right? You remember OD is equal to OA, and that is your radii. Then you can say but A1 is 57 degrees, and then I know that angle D is made up of D1 plus angle D2, right? So it's now just a matter of me finding what? Of finding D. If I can get D1, then I would have gotten D2. I look at D1 and say it's equal to which other angle? Look at D1, it's formed by this chord AB, right? And that very same chord is forming another angle at the circumference, which is what? Which is angle C. So it tells you that D1 is equal to angle C, and both are 33 degrees. Why? It's still saying angles on the same what? Angles on the same segment. Then you can then say 57 degrees will be equal to the 33 degrees plus the D2. Then you'll be able to solve for D2. I think you should get it as, I don't know, is it 24? 24 degrees, yeah. So D2 will be 24 degrees. And then if they say show that AE bisects DAB, it means that show us that A1 is equal to A2. Luckily enough, one of us already had proved that A2 is 57. So therefore, AE does bisect DAB, right? This is DAB. So it's bisected because those angles will be equal. So it will be a very much easy question. All right, we are still going to do more, guys. I hope that this has been helpful. I will see you on the next one.